All right, today we're jumping into one of the most classic puzzles in all of physics, and we're going to solve it using the power of second-order differential equations. This is where the abstract math you learn in class gets incredibly real. We're talking about predicting the motion of everything from a simple spring to a skyscraper swaying in the wind. It's the perfect playground to see these equations come to life. So picture this. You've got a mass hanging on a spring. You pull it down, you let go, and it starts bouncing. Seems pretty simple, right? But here's the real question. Could you write down a mathematical formula that tells you exactly where that mass will be at any moment in time? The answer is a resounding yes, and figuring out how to do that is exactly our mission today.
So here's our game plan. First, we're going to build the fundamental equation of motion from the ground up. Then, we'll see what the system does all by itself, in a perfect world. After that, we'll introduce the real-world effect of damping. From there, we'll get to the really cool part. What happens when we start pushing the system, which leads to the incredible phenomenon of resonance. And finally, we'll run through some practical examples to make sure it all sticks.
Okay, section 1, the equation of motion. Before we can solve a single thing, we need to translate our physical setup, the mass, the spring, all of it, into the language of math. We've got to build our formula. And here it is. This right here is the heart of everything we're going to talk about. It's a second-order linear differential equation. And the best part is, it comes directly from one of the most famous laws in physics, Newton's second law. You know the one, force equals mass times acceleration. Now, it might look a little intimidating, but each piece just represents a specific physical force. That first term, mu double prime, well, that's just your inertia, straight out of F equals ma. The next term, gamma u prime, that represents any damping forces, kind of like air resistance or friction, that work against the motion. Then you've got Ku, which is the spring's own restoring force, the part that's always trying to pull the mass back home to its resting position. And last but not least, F of t is any outside force that we might be applying to the system. All right, moving on to section 2, free vibrations. To really get a handle on this equation, let's start with the simplest possible case. What happens if we just pull the mass back and let it go, with no friction and no one pushing on it? This is what we call a free vibration. So in terms of our equation, this is super easy. We just set that external force, F of t, to 0. Gone. Now the way the mass moves depends only on its own built-in properties. Its mass, how stiff the spring is, and of course, how we started it all off, its initial position and velocity. And if we take it one step further and imagine a perfect world with no damping, so our gamma term is also 0, we get the purest kind of vibration there is, simple harmonic motion. The system would just oscillate back and forth forever. And the speed of that oscillation is what we call its natural frequency, or omega naught. That frequency is determined only by the spring constant k and the mass m. It's the specific rhythm the system just wants to vibrate at. Of course, in the real world, nothing bounces forever. Energy always gets lost to things like friction and air resistance. That's damping. So let's add that gamma term back into our equation and see how it completely changes the game. Adding damping gives us 3 new possibilities, and it all depends on how much damping there is. If the damping is pretty light, we get an underdamped system. It still bounces, but the bounces get smaller and smaller over time. If the damping is really heavy, it's overdamped. The mass just slowly oozes back to its resting spot, almost like it's moving through molasses. But right in that sweet spot between them is critical damping. This is the fastest way to get back to equilibrium without overshooting. It's exactly what you want in a car's shock absorber. And the key to figuring out which case you have is this little expression right here. Gamma squared minus 4mk. It's the discriminant from the characteristic equation, and its sign tells you everything. Now, let me give you a huge tip. A super common mistake on exams is forgetting to square the gamma. That tiny little exponent makes all the difference, so don't forget it. All right, we've seen what the system does on its own. Now for the real fun. What happens when we add that external force back into the mix? What if we start pushing on the mass over and over again? And let's get specific. We know the system has a favorite frequency it wants to vibrate at, that omega naught we talked about. So what do you think happens if our external pushing force has that exact same frequency? This, my friends, is the condition for resonance. When your driving frequency perfectly matches the natural frequency in an undamped system, something wild happens. The amplitude of the motion just grows and grows. The equation for it looks like this. Now, at first glance, it just looks like another sine wave, but I want you to look really closely. Do you see that one single letter in there that changes absolutely everything? It's this one, the T for time. Notice how it's sitting outside the sine function, multiplying the whole thing. What does that mean? It means the amplitude isn't constant anymore. As time t gets bigger, the amplitude just grows with it, linearly, forever. This is why a tiny periodic push can make a bridge collapse. It's why an opera singer can shatter a wine glass. This is the math of catastrophic failure, and it's all because of that one little t. Okay, section 5. That's a lot of theory. Let's make it more concrete. How do we actually use these equations to solve the kind of problem you might see on a homework assignment or an exam? So here's a classic setup. First, we need to find the spring constant, K. We can do that just by realizing that when the mass is just hanging there, the spring force, KL, has to perfectly balance the force of gravity, mg. That's step 1. Next, we put together our differential equation and our initial conditions. We know it started 0.2 meters down and was released from rest, so its initial velocity is 0. Finally, we solve that dE, plug in our conditions, and boom, we get the unique equation that describes the system's motion for all time. Now, sometimes the problem works the other way. You're given the solution and you have to interpret what it means. Well, as soon as you see an exponential decay term and a sine term, you should be thinking underdamped. The number inside that sine function, the 4, that's what we call the quasi-frequency. And from there, it's super easy to calculate the quasi-period, which is just the time it takes to complete one decaying oscillation. And for our last example, let's nail down that concept of resonance. To find the resonant frequency for this system, all we need is its natural frequency. We can just look at the equation and see that the mass m is 1 and the spring constant k is 9. We know the natural frequency is the square root of k over m, which is just the square root of 9, so it's 3. That means resonance will happen if and only if that driving frequency omega is also 3. It's really as simple as that. So let's wrap this up with the most important takeaways. First, all this complicated bouncing and shaking boils down to a single, powerful second-order differential equation. Second, the type of motion you're going to see is determined entirely by that one key expression, the discriminant. And finally, the most dramatic result, resonance, happens when you push a system at the exact frequency it already wants to vibrate at. Now, we've been focused on a simple mechanical system, but this idea of resonance is everywhere. It's why some buildings are especially vulnerable to earthquakes, it's how an MRI machine works, and it even plays a role in the orbits of planets and moons. So the question I want to leave you with is this. Now that you understand the math behind it, where else in the world around you can you spot this powerful principle at play?